Welcome to the 44th Theoretical Physics Colloquium. This is also a joint cosmology seminar at Arizona State University. And I'm glad to present our speaker today, Gordon Baym, who's a research professor at the University of Illinois at Urbana-Champaign. He received his PhD from Harvard University. After several postdoc positions, he became a faculty member at the University of Illinois, where he remains until now. He has numerous awards and honors, and I would not be able to even list them all. Let me just mention that he was an Alfred Sloan Foundation Research Fellow, Alexander von Humboldt Foundation Fellow. In 1968, he became the Fellow of the American Physical Society. In 1982, member of the National Academy of Sciences. In 1993, he was elected Fellow of the American Association for the Advancement of Science. He received Hans Bether Prize from the American Physical Society in 2002. In 2008, Lars Onsager Prize from the American Physical Society. And finally, in 2021, this year, he received the APS Medal for the Exceptional Achievement in Research, the site in red, for major discoveries in theoretical condensed matter and many-body physics, neutron structure and composition, quark matter and quark-gluon plasma physics, and in atomic physics in ultra-cold quantum gases. He did a lot of service for the community. He's an associate editor of nuclear physics. He used to be a member on the editorial board of the annual review of nuclear and particle science, member of the editorial board of the proceedings of the National Academy of Sciences. He's on the editorial board of Heavy Ion Physics, Acta Physica Hungarica. He's a member of advisory committees of numerous national and international organizations, and obviously his field of research is extremely wide. And today he will be talking about the evolution of primordial neutrino helicities under gravitational and magnetic fields and implications for their detection. And with that, I'll give the microphone to Gordon.
Thank you, Igor. Thank you so much for the glowing introduction. I noticed the citation from the that APS medal didn't mention the word neutrinos or cosmology, but for since I was locked down all year, I decided I was try learning some new areas. So with my colleague, the experimentalist Zhenxi Peng in Urbana, who's a very noted neutrino experimentalist, I began learning about neutrinos from the early universe, the interesting problems they pose. And also from our co-host today, Tanmay, I began to learn something about magnetic fields in the universe as well. So I'm really grateful to both of you for being my instructors this past year. Prior to about 1 second after the Big Bang, neutrinos, and there are three of them, electron, muon, and tau neutrinos, as well as antineutrinos, they cease to be in thermal equilibrium with the matter. And since about a time of about 1 second after the Big Bang, the neutrinos have been free streaming through the universe, almost free streaming through the universe en route to us. And it's important to realize there are a lot of these neutrinos. I mean, there's a density of 56 neutrinos per cubic centimeter of each of these three, each of these various species here. Too many here. Mu should not be repeated. And this is about 100 times as many neutrinos as come from the sun. And what's interesting about these neutrinos is, in your body, you have at the moment something like 20 million, depending how much you weigh, 20 million neutrinos from the Big Bang. This is much more impressive than what's left over from the cosmic microwave background, which is basically shielded from the atmosphere. And what's interesting about these neutrinos, even though there are so many of them, they've never been detected here. And so that is a major challenge for experimental physics to detect these primordial neutrinos. Okay, what I want to discuss is what happens to these neutrinos between the time of 1 second when they became free and now 13 so almost 14 billion years later. Now, what we know about neutrinos from weak interactions is that neutrinos have negative helicity. They're left-handed, which means the spin points opposite to the momentum. Antineutrinos have positive helicity, which means their spin is parallel to their momentum. Now, what's important to realize is the helicity of neutrinos is not a property of neutrinos themselves, but is rather a property of the weak interaction processes that produce the neutrinos. What I want to focus on in this talk is the fact that galactic and cosmic and galactic magnetic fields, as well as gravitational inhomogeneities, can rotate the spins with respect to their momentum. And thus, if these arrows don't point exactly backwards or forwards, the neutrinos would have a neutrino would have an amplitude to be right-handed, and an antineutrino would have an amplitude to be left-handed. And the basic message is that the helicities of the relic neutrinos, which are modified as they pass through the cosmos, are a new probe of cosmic gravitational and magnetic fields, a probe that's independent of the cosmic microwave background here. And so this is a potentially interesting new area of physics. The current experimental technology is not up to it yet, but it will happen. Okay. So here's a general outline. I want to give a quick crash course in neutrinos, Neutrinos 101. I want to talk about neutrino magnetic moments and spin precession, how gravitational inhomogeneities cause spin precession. And finally, if there's time, I'll talk about the detection of relic neutrinos. This picture here is you probably have all seen this, of this supposedly medieval picture of the Earth and the interested scientists peering through way back to see how the gears of the cosmos work. This is actually an interesting picture. It was created in 1888 to look medieval, but it's actually quite a relatively modern creation. Yeah. Okay, so if we start back prior to a second after the Big Bang, and the relation between temperature and time is that time in the early universe was roughly, time in seconds is roughly 1 over the square root of the temperature in MeV. Lots of processes kept the neutrinos in equilibrium. Neutrinos scattered from electrons. They also scattered from the heavy leptons and muons and taus until they froze out at temperatures which are much higher than 1 MeV. So, but the scattering from electrons, positrons keeps them in equilibrium. They scatter among themselves. In addition, there's pair-annihilation processes. Nu plus nu bar goes to E plus E minus. But for the electrons, there's something very special, which is the charge exchange interaction through exchange of a W. That a neutrino plus an electron, they can change places. The neutrino becomes an electron, the electron becomes a neutrino, and the same thing with antineutrinos as well. These processes, because they're special to the electron neutrino, they will keep the electron neutrinos in equilibrium slightly longer. And so one finds out that the neutrinos decouple simply because the universe expands, the distance between particles becomes larger than the mean free paths, and at that point the neutrinos cease to be in thermal equilibrium. And so you find the muon and tau neutrinos decouple at a temperature of around 1.5 MeV, but the electron neutrinos decouple at around 1.3 MeV. This is not an important difference for what comes later here. Okay. Now, what's interesting is that neutrinos have a finite mass. I'll say more in detail about this. And because of this finite mass, they have a magnetic moment. Because they have a magnetic moment, their spins will be rotated in cosmic magnetic fields and galactic magnetic fields. Because neutrinos do not have a charge, however, their momenta will not be rotated by the magnetic fields. And so simply a neutrino with a magnetic moment in a magnetic field will find its helicity being slowly modified. In addition, gravitational potentials can rotate momentum and spin differently. And the simple example is suppose you take a neutrino and throw it up in the air, throw it straight up in the air, a non-relativistic neutrino, and throw it up at less than escape velocity. It will go up, turn around, and come back, but its spin will not rotate. If it goes up here as I showed it here, as a right-handed particle, it will come down as a left-handed particle. This is for non-relativistic particles. In fact, the rotation of spins by gravitational fields is entirely a relativistic effect here that involves both the gravitational potential and the speed of light here. So the relative bending of spin, the standard equation for the bending of momentum is velocity plus 1 over loss velocity times the gradient of the gravitational potential. And for the spin, it's 2 gamma plus 1 over gamma plus 1 times spin dotted velocity. And gamma is just the Lorentz gamma 1 over the square root of 1 minus v squared, velocity squared. And these are different. And so what you find is if you look at the difference between the spin bending and the momentum bending, you find that this goes as a mass divided by momentum times the gradient of the potential. So the spin and momentum are bent differently, which means that gravitational fields will also change the gravitational fields will also change the helicity of the particles. Okay, a simple example is suppose you send a neutrino or any massive particle past a star of mass m, say, at impact parameter b. Then the angular momentum, the momentum will change. The angle, that's this difference here, will change by 2mg over b velocity squared 1 plus velocity squared. If you let velocity go to 1, the speed of light, this 2 becomes a 4, and that's just the Einstein bending of light. If you look at the spin bending, however, it is smaller, except in the fully relativistic limit, where gamma gets very large, and so this again just becomes 4, the same coefficient. And so for a fully relativistic particle, a massless particle, the spin and the momenta track each other completely. This is true for photons, but true for any other massive particle that might appear. Okay. Well, this bending gives rise to helicity change. And so what happens is as the spin angle changes with respect to the momentum, if a neutrino starts to spin down, it will develop an amplitude to have spin up with an amplitude to sine theta over 2, and to stay down, it's cosine theta over 2. So the probability of its helicity changing is just sine squared over 2, sine theta over 2 all squared with 1 minus cosine theta over 2, or for small angles, which we'll be talking about entirely, this is just theta squared over 4 here. Okay. Now, neutrinos are rather complicated beasts. Neutrinos in weak interactions are made and absorbed in flavor eigenstates, electron, mu, and tau neutrinos. However, the natural mass matrix, mass states in which they propagate, are somewhat different. There's states nu1, nu2, nu3 by common notation, which have different masses. This is called the PM and S matrix. It's a unitary matrix that relates the flavor eigenstates to the mass eigenstates, to the mass eigenstates, the flavor states, not flavor eigenstates, to the mass states here. Actually, my colleague Zhenxi Peng is responsible primarily for measuring the UE3 component of this matrix here at diap A. Okay, now what's happened is you make neutrinos in your early universe, they scatter, and at the last scattering, they come out in the wave packet. The characteristic size of a wave packet is probably of order the electron mean free path, which is of order 10 to the 6, 10 to the 7 Fermi. And they come out with a velocity p over square root of p squared plus m squared. Now, m here, they're made as electron states say, m here will involve 3 different mass eigenstates, and so there'll be dispersion in the velocity. And if you calculate the dispersion of velocity, this is rather large. Typical velocity dispersion is delta m over m times mass squared over momentum squared. There's also dispersion because the momentum is not precise, but that's actually much smaller. So the result is what happens is the neutrino, though it's made in a flavor eigenstate, will quickly disperse into 3 well-defined mass eigenstates, each of which has a well-defined mass, and that's how neutrinos will propagate across the universe. And so if you look at the distribution, the momentum distribution that we see on Earth now, this will involve this matrix that tells you how a given flavor A projects onto a mass eigenstate divided by, this should have various eyes decorating it, divided by distribution. Now, I want to focus on this distribution for one moment because it's got some funny features. But let me first mention neutrino masses. We have evidence for neutrino masses from the neutrino oscillation experiments, SNO and T2K. And what you find is we know there's a pair of neutrinos here whose masses are separated as mass squared, 7.5 10 to the minus 5 eV squared. And there's a third neutrino, which is well separated from this other pair by 2.5 times 10 to the minus 3 eV squared. What we don't know, however, is this state higher? This is the normal hierarchy, or is M3 lower? That's the inverted hierarchy. And so one sees these various cartoons. The big mystery is neutrino 3 the heaviest, or is it the lightest neutrino of the batch? So coming back to this picture, this is the same mass distribution. I show here the neutrino temperature, the present neutrino temperature. What you see is that two of these states, whether in the normal or inverted hierarchy, two of these states are above the temperature. The masses are above the temperature, which means these neutrinos are non-relativistic now. In fact, if you calculate velocities, the present neutrino temperature is about 2 Kelvin, or 10 to the minus 4 electron volts. If you take the lowest mass here in the normal hierarchy, if you take the lowest mass at 10 to the minus 5 electron volts, then the state 1 is fully relativistic, but 2 has a velocity which is a fifth the speed of light. The third up here has a velocity which is 20th the speed of light. Similarly, in the inverted hierarchy, if you again call this 10 to the minus 5 eV, then this state is purely relativistic, but these two up here have velocities which are closer to 1/20th the speed of light here. So neutrinos are, two of the three species, masses of neutrinos are non-relativistic now. Okay. What's interesting also is that the neutrino temperature is below the cosmic microwave background, and that's not a property of the neutrinos. That's a property of the cosmic microwave background photons, because when electrons and positrons annihilated, they gave their entropy to the photons and reheated them. And so the cosmic microwave background has undergone reheating, whereas the neutrinos have not. Okay, so if we look at the distribution, electron-neutrino distribution at decoupling, then a given electron neutrino will separate into mass eigenstates, and each of the probabilities will go as p squared plus mass I squared. However, the momentum at on the MeV scale decoupling was the masses are on 10 to the minus 2 electron volt scale, and this is approximately the momentum. And so the neutrinos, when they're made, appear to have a relativistic distribution. And because the neutrinos do not interact, they preserve the distribution. And so one has a peculiar situation as neutrinos arrive at Earth, these 20 million that are inside of you, they have a relativistic distribution of momenta. However, two of them are non-relativistic. Were they have to stay in equilibrium, then the momenta would scale as the scale factor of the universe grows from a small universe to a large one. I'll be more detailed about this. The momenta scales as 1 over the A, and temperature scales as 1 over A. And so what you would find is that the initial distribution back here goes p squared over m squared. If you put in the A factor, you find this to be p0 squared plus m squared A squared. And A is now 1, and so you would find that you would have a non-relativistic distribution here. Okay. Okay, now let me just say one quick word about the cosmology, the background. The metric of expanding universe, if one has weak gravitational inhomogeneities, one can write it in terms of conformal time, which is dt, this is the time in your wristwatch, is the scale factor, that's the thing in front of this metric here, times the conformal time. And so there's an A out front. There's a 1 minus 2 phi, where phi is the weak gravitational potential, and the spatial component has a 1 minus 2 phi here. This looks almost like what you get if you just expand the normal Schwarzschild metric, but some slight coordinate differences here. And the x's here are co-moving spatial coordinates. Okay, now This weak gravitational potential is driven by both density and pressure fluctuations. The gradient squared with respect to the co-moving coordinate is g, the gravitational constant, 4 pi rho, the density fluctuations, and 3 times the pressure fluctuations times a squared. In the matter-dominated universe, that's the more recent one, the pressure is negligible. But generally what you find is that the density fluctuations times a squared are independent of the scale factor, which means that phi of x is independent of the scale. It remains, in terms of co-moving coordinates, it remains constant, at least at long wavelengths. Now, in the radiation-dominated era, where the pressure is a third of the density, then what you find is from linear perturbation theory is that delta rho over the mean rho goes a squared, and rho goes a to the fourth. So you find this delta rho goes a squared. Delta rho a squared is constant. And in the matter-dominated era, you find a similar result here. Okay. Now let's turn to neutrinos and their magnetic moments. Because neutrinos have a finite mass, they have a magnetic moment. And the simplest processes that give rise to a magnetic moment were detailed by Fujikawa and Schrock in 1980, and other people saw similar effects. But I think they're the first who actually used the word magnetic moment here. And just a process where a neutrino comes in, emits a W, which can then couple to a photon, or the intermediate neutrino here. The intermediate lepton here can be charged, and that also couples to photons. And there are various processes like this. And you add these all up in the standard model, where you assume the neutrino has a mass, and you find some very simple result. That you find a magnetic moment 3 times E, the charge in the electron. GF is the Fermi weak interaction constant. We'll see a lot of that guy later. And times the mass of the neutrino. And if you measure this in terms of the Bohr magneton, and measure the neutrinos in mass characteristic scale of 10 to the minus 2 electron volts, you find this is 3 10 to the minus 21 times m minus 2 times Bohr magneton. It's very small. However, the magnetic moment could be much larger. And this would, of course, involve physics beyond the standard model. People have measured upper bounds on the neutrino magnetic moment. There are 2 experiments. In Russia, there's a reactor experiment called GEMA, which looked at antineutrinos on electrons and gave an upper bound for the magnetic moment of the neutrino as 2.9 10 to the minus 11 Bohr magnetons. Notice that that's a factor 10 to the 10 larger. There's a lot of wiggle room in this game. Similarly, the Boraxino in Gran Sasso, looking at solar neutrinos, so we're able to give a bound for the electron magnetic moment, the magnetic moment of the electron neutrino, of 2.8 10 to the minus 11, same number basically. And again, a factor 10 to the 10 larger. There have been considerations, since what you see here is that the magnetic moment is proportional to the mass of the neutrino, and people have asked, how big could this coefficient be? And this is called the naturalness bound. And they concluded maybe it's 10 to the minus 16 instead of 10 to the minus 21 here. However, the other physics could say maybe it's not right that the magnetic moment scales with the neutrino mass, maybe it scales with the lepton mass. And so it could be substantially larger here. Now, one important technical feature, one has to distinguish diagonal versus transition magnetic moments. And the question is, as a neutrino comes in and emits a photon through coupling through its magnetic moment, does it come out with the same mass state or not? Diagonal magnetic moments are ones where interaction with the magnetic field does not change the mass state. Transition magnetic moments are ones that change the mass state. So here, the mass of 1 is mass of 2 for diagonal, and for the transition, the mass of 1 is different. Mass of the first neutrino is different from the mass of the second. Now, the reason this is important is one of the big questions is whether neutrinos are Dirac or Majorana. Dirac neutrinos can have both diagonal and transition moments, whereas the diagonal moments of Majorana neutrinos, as you can see from a simple CPT argument, can only have transition moments here. What that means, as neutrinos propagate through the cosmic, galactic, and magnetic fields, there's not enough energy in the process to change the neutrino mass state. And so only the diagonal magnetic moments can affect the neutrino spins, transition magnetic moments cannot. And what this is Majorana neutrinos are not affected by cosmic magnetic fields. Their spin is not affected by cosmic magnetic fields, but Dirac neutrinos are. They can have their helicities changed by cosmic magnetic fields here. Okay. There's been this interesting experiment, the xenon 1 ton experiment, which is a ton of liquid xenon, which sees both looking for particles coming in, seeing both electron and nuclear recoils. They're searching for WIMPs, other dark matter, and they're really sensitive to physics beyond the standard model. They look for solar axions, bosonic dark matter, and also have possibly detected magnetic moments of solar neutrinos. And the evidence is at low energy, these are energies for 7 MeV, 0 to 7 MeV, these electron events, what they see up down here is an excess over the background. And this is significant, this excess here. This was published, this data came out in the spring this past year. Here's the picture over here again. And there are three possible explanations that xenon 1 ton have come up with. One is one could be seeing a large neutrino magnetic moment. Where that one functions as a neutrino magnetic moment would couple to the electrons, give an additional to the coupling to the electrons, and so increase the rate of electron events here. It could be solar axions, and it could be something much more mundane, which is tritium contamination of the xenon, the beta decays of tritium here. One doesn't know. But it is possible that one is in fact seeing evidence of a large neutrino magnetic moment. This is a picture showing the bounds on neutrino, and this is where xenon 1 ton magnetic moment would live here. This gives a bound something between a neutrino magnetic moment 1.4 and 2.9, 10 to the minus 11. Again, this is the same factor 10 to the 10 larger than the standard model here. Now, some people may argue there are various cosmic bounds on neutrino magnetic moments. Tanmay is more of an expert on this. Everything I know about this, I learned in his lovely review article in Reports on Progress in Physics here. How certain those bounds are is unclear. And so if you look at the particle data tables, they list these two, the experimental bounds, but not any astrophysical bounds. Okay. So the spins will precess in magnetic fields, but the momentum does not. And so they're changing neutrino helicity. And the question is, how do we calculate this? If you're in the rest frame, one has a simple spin rotation with the magnetic moment coupled with the magnetic field. Now, it's important to think about what frame you define the spin in. And it's conceptually simplest, and I will not get into that question, to define the spin in the rest frame of the neutrino. However, it's convenient to work, most convenient to work in the laboratory magnetic, with a laboratory magnetic field, which is related to that's the plane B's, which is related to the spin in the rest frame by the longitudinal field is the same, but the transverse field has a Lorentz gamma in it here. So the equations of motion that govern the spins that govern the spin in the rest frame in terms of the laboratory fields are the Bargmann-Michel-Telegny equations, the BMT equations of motion, which is S parallel cos B perp. The perp stands for perpendicular to the velocity of the neutrino. And this term has, the parallel has a 1 over gamma, and this is generally negligible if S perp is already small to begin with here. BMT, I like the name BMT because it reminded me of my childhood of the Brooklyn-Manhattan Transit, which is one of the main subway lines in New York City before they unified the system there. Okay, so the question is, how do we calculate the spin rotation? If we look at the spin, the transverse component of the spin looks at small angle changes. If you look at the transverse component of the spin divided by the total spin, this from here will be plus or minus twice the magnetic moment, depending on helicity, times the integral along the path, dt, times the velocity, the component of the magnetic field transverse to the velocity. Okay, and so what I want to do is take this equation, apply it to both galaxies and cosmic magnetic fields. Okay, here's a picture of a magnetic field in a galaxy. Now, I am not an expert at all on galactic magnetic fields, and so I'm going to be tremendously oversimplified here. But what you see in this picture, however, is this is the Whirlpool galaxy, M51. It's a beautiful Hubble photo. Superimposed on this are magnetic fields, which are deduced from the SOFIA mission, which is an infrared detector which flies on a big 747 airplane, flies within the atmosphere. And the field lines here are superimposed on the Hubble image. And the one thing you can see here is that the fields are not very uniform. The fields are not uniform across the entire galaxy. Rather, what you see, if you look over here, in this region here, you see, well, the fields are fairly uniform, but as you move away, they change, and the direction of the field tends to change. Namely, the fields in galaxies have a coherence length here. And so if we begin to calculate the spin rotation by a galactic magnetic field, if it's a uniform spin, then you say that, well, the rotation is just magnetic moment times the field times the travel time across the galaxy. Let's say L is the mean crossing distance, V is the velocity. But because the galactic magnetic fields are not uniform, that's coherence length lambda, what the spin will do is a random walk. So within the distance lambda, you have a spin rotation given by lambda over V, but then the mean square will be the spin rotation. The mean spin rotation squared will be the rotation squared per event, per coherence length, times the number of coherence lengths in the total length here. It's just a standard random walk. And so what I want to do is just estimate this in the spherical galaxy, or as theorists like to call it, the spherical Cow approximation here. So let me take just roughly a galactic field of 10 microgauss, a size of 16 kiloparsecs like Milky Way. That's our distance from the center of the Milky Way. And a coherence length about a kiloparsec. And what you find is a rotation angle, which is 4/10 to the 29 times its characteristic parameters, mass, the mass of the neutrino electron volt squared. The mass enters this because the velocity depends on the mass here. And mu nu, the magnetic moment divided by in units of the Bohr magneton squared. And so if you take a value of the neutrino magnetic moment 10 to the minus 15, which is about 10 to the minus 4 of the value that was maybe found in the xenon one-ton experiment, what happens is there's this little bar from Zoom gets in the way of the slides. This gives you a mean rotation angle, something to order 1, which says that even this size magnetic moment of neutrino going through the galaxy, the neutrino helicity could be completely randomized here. Okay, so these could be potentially large effects here. Oops, where am I? I'm sorry, my slide skipped ahead for some reason here. Okay. Now how do we let's ask the question, what happens to the spin as we propagate through a cosmic magnetic field? And again, cosmic magnetic fields have finite coherence lengths. And so one can ask for the spin and rotation angle, that's the absolute value of this thing. The angle squared is the absolute value of the transverse field divided by transverse spin divided by total spin squared. And that's 2 mu squared, 4 mu squared. And you integrate the transverse field along the path motion. And this becomes the integral dt, which is dua, A is a scale factor, times the perpendicular velocity. You evaluate that squared. Now, this clearly will involve the magnetic field correlation at different points. The magnetic field correlation, as I learned from Ptolemy's review, comes in 2 different components. There is a normal component, which has a projection operator here, which guarantees the divergence of the magnetic field is 0 times F. And then there's a helical component, epsilon ijk, gradient k here. And Axel Brandenburg, who's sitting in the audience, is one of the experts on the structure of the helical components of the cosmic magnetic fields. And so any questions, I'm sure Axel will be very happy to answer them here. What is interesting, however, is that the helical contribution here does not in fact contribute to the spin rotation here. And what matters is really just the normal correlation function component here. And so the BI, we'll focus on BI/BJ as involving just the transverse projector here times a spectral weight P times Fourier transform. Now this, Ptolemy in his review and generally works with a slightly different notation for the spectral weight of the galactic field. He uses E, and E defines from factor 2 pi. E over k squared is just P over here. So here's a picture again from Ptolemy's review article, which is in the archive here, showing that at early time he uses eta instead of u, but this is the conformal time. At early time, schematically, the correlation function was up and then it comes down. As time goes on, one moves this way, the height drops and the momenta moves, the maximum wavelength, maximum wave number moves to smaller values as well here. The general structure, this is the same picture again, the general structure is that if you're below this critical, the maximum here, it goes roughly, is k to some power. The power is probably something of order 2. And at higher values, it falls off with something like k to the minus q, which looks like roughly a Kolmogorov 5/3 for big E here. Also, the P obeys the sum rule, which is if you integrate overall momenta, P is just the magnetic field, mean value of the magnetic field squared. So I don't want to go into the details. The details are on the slides, but as you integrate the magnetic field across a long trajectory, you have this more complicated integral here. And what you find is that the mean field rotation angle squared goes to magnetic moment squared, the integral of along the path of the scale factor squared, and integral dk times k of the momentum of the spectral weight. This integral involving the spectral weight, if you take this structure like this, you find it goes basically as the magnetic field squared from the sum rule divided. This is missing a momentum, and the characteristic momentum in case the maximum comes out over here. So one finds an angle squared going as mu squared times this integral b squared over k star. Okay, now the next question you want to ask is how does this vary as the universe gets older, as time passes in the universe? And this is the same equation here. Flux is roughly conserved. I mean, this is an oversimplification. There are various dynamo mechanisms that will increase the magnetic field. But if you be most naive and just say as a magnetic field, as the universe expands, the field lines expand, and this says B will fall off as 1 over a squared. And so this, a squared B is roughly constant here. Yeah, this is B and this is B squared here. And so it says B squared is going as B naught squared, the value now, divided A over the 4th. The coherence length, as I learned from Ptolemy, is estimated to go something like 1 of the scale factors of the 1/2 here. And lambda naught here is a length which is the present coherence length of the cosmic magnetic fields. Coffee time. So you put this all together, you find the angle, mean spin rotation, goes as the integral of a of u to the 3/2 power downstairs. Now, because it's got an a downstairs, and a was very small in the early universe, the main contributions to the radiation-dominated era were a scales as the conformal time. And so this is the time for neutrino decoupling when a was 10 to the minus 10, to matter radiation equality when a is about 10 to the minus 4. And you put this all together and do the integrals, and you find that these bending angles like 10 to the minus 10 to the 27, this is quite comparable to what we had in galaxies, assuming a magnetic field of intergalactic field of 10 to the minus 12 Gauss, and again, magnetic moment squared, and a coherence length of about a megaparsec. So the general scales for galactic and magnetic bending are pretty comparable here. So the conclusion of this is that the bending angles, if the neutrino excess, the low energy electron event excess found in the Xenon 110 experiment, does in fact come from a neutrino magnetic moment, it could lead to significant spin rotation. Even if it's as small as 10 to the minus 3, if magnetic moment is as small as 10 to the minus 3 of the Xenon 1 ton result, this is 10 to the minus, magnetic moment 10 to the minus 14. This could have significant randomization of the helicities as the neutrino goes to cosmic galactic fields. Now, again, I stress that if the neutrino is Majorana, the Xenon 1 ton excess would occur entirely from transition magnetic moments, and Xenon doesn't tell us whether it's seeing transition or direct or diagonal magnetic moments. And so there would be no helicity changes from the magnetic fields. And to within the uncertainties of magnetic fields, correlation lengths, neutrino masses, the estimated spin rotation from both the cosmic magnetic fields and galactic magnetic fields are basically comparable here. Okay, let me just rest for a moment and ask for any questions. People have questions at this point.
This is Paul Davies here. I have a question.
Yeah.
Let me come on to it relates to exactly what you're showing about gravitational inhomogeneities. One of your most striking illustrations was if you throw a neutrino up in the air, it comes back down with a reversed helicity.
Yes.
But that looks like it would be true even in a uniform gravitational field, which would not have a curvature, space-time curvature. So if it's just, a little g, and it's a constant field, the particle would still go up and come down, but there would be no gravitational inhomogeneity, no space-time curvature.
I'm not sure I agree. I mean, if we're going transverse to the gradient, I think there will be rotation.
But if you go up and come back down, I thought that was a really nice slide.
Oh, no, if I go parallel to the gradient, yeah. If I go parallel to the gradient, nothing happens. Yeah, I agree.
Oh, okay. All right. Thanks for clarifying that.
Yeah, okay. But I will. But next part of the talk, I will focus on the gravitational inhomogeneities.
We also have a question from Kohei.
Okay.
So can I sorry to ask a question? So for the cosmology, for the cosmic magnetic field, when is the most effective spin rotation happens? At the generation of neutrinos or at present?
Oh, I'm sorry. I don't understand the
So
sounds.
my question is that this is
Igor, do you understand the question?
Only part of it. For
Okay.
cosmological magnetic field, you said. Sorry, the last part I did also miss.
So my question is, when the spin rotation is most effective, at the early time or at present?
In the gravitational fields, it's a later time. In the magnetic field, it's the early times that dominate.
Then can we see? So is it sensitive to the generation time of neutrinos, or when? So the temperature of the generation time could be different. So the reheating temperature it might be related to reheating temperature of the universe.
So the question is about the temperature at which this was happening. It might be relevant as far as I understand.
No, because the neutrinos are not interacting. They don't sense the temperature. They're just flying with a given momentum from the time they were released to now. The momentum is scaling down because of the expansion of the universe, but there's no interaction of the neutrinos with anybody else. No significant interaction.
I don't mean the temperature itself, but the initial time itself.
Oh.
The time.
Yes. So certainly if the neutrinos decoupled, at let's say 100 seconds rather than 1 second, that would make a noticeable difference. Yes.
Yeah. So perhaps it would be it might be able to detect the time. If we are able to look at the spin rotation, then we might be able to see the initial time.
This will probably be an interesting PhysRev letter in the 2060s. We're not ready for that. Okay. Well, thank you very much.
Okay, another question from Jin Young one.
Yeah, this is a very quick clarification. Is this magnetic field part of the microwave background radiation, or it's not?
No, these are basically quote static fields. These are not high frequency fields at all.
Okay.
Yeah.
Okay. I will have a question come back later.
But your other question is very good. I mean, once you ask the question that there is the cosmic microwave background.
Yes.
Has magnetic fields associated with it,
yeah.
Which you can get very simply by saying B squared goes to the temperature. And so there's another calculation to be done there. And
yeah,
so,
I think that this is a very straightforward question. I mean, if you consider scattering of neutrinos, with other, like for example, micro background radiation, other field, that can also cause spin rotation. I mean, not a spin rotation, but randomization probably too.
Yeah, it's probably much weaker though. But
I see.
I'd say probably.
Okay. Thanks.
Thanks. Okay, now let's turn to gravitational inhomogeneity. The basic equations are the gradients of the field drive momentum direction, but they change the spin direction, and these are different. Okay, so again, the neutrino goes a random walk through the inhomogeneities, and a similar argument, you calculate the momentum squared, angular change in momentum squared, the square of the angle, momentum change all squared, and you integrate along the path and gradients, and you can write this in terms of the gravitational fluctuation power spectrum. If you write phi is some psi of k in Fourier transform here, and I'll repeat this on the next slide here. The equation is repeated here. Then what one finds is you integrate this in the same way. I'll leave out the details, and you find that the angle squared is going as the integral along the path, conformal time, times dk over k, same structure that we found for magnetic fields, but now in terms of the gravitational fluctuation spectrum. Now, if we relate this to the density fluctuation spectrum, delta rho over the mean rho, the fluctuation spectrum is labeled P, and what you find is very trivially, psi is related through because of the equation of motion. Psi is related in terms of G, Newton G times mean rho, A squared, P of P over K to the fourth. This factor zeta comes from the fact that in the radiation-dominated era where the pressure fluctuations are 1/3 of the density fluctuations, one is a net factor 2 here, 2 squared is 4. And in the matter-dominated era where the pressure doesn't enter, this is just 1. So there's this extra factor here, which is trivial. Okay, now the density fluctuation has actually been measured by Planck in great detail. And what they find is the P of K here goes as K, rises linear, it's a Harrison-Seldovich spectrum, up to a maximum value. Then it falls with a power, something like 2 or 3 or 4 here. And also scales in the matter-dominated era, which is important, as A squared. So as A goes on, this fluctuation spectrum will rise here. And so you put this all in the integrals, and what you find eventually, it's easiest to, in this case, since we have very good data for the fluctuation spectrum, it's easiest to do the integral numerically, and you find that the P has units of a length cubed, and so this is some 10 to the 4th megaparsecs cubed divided by H is represents our uncertainty in the Hubble parameter, and H is something like 0.7 here. So the result, you find the angle squared is going as 1 over U0 is the conformal time now, which is 3 times the age of the universe now, times integral decay over K. So we have a fair idea what this angle is here. And so what this tells us is that we have a guess for what the mean bending, and we can think of this in terms of if you think of gravitational lensing, what we're seeing here, it's calculating here is gravitational lensing of the cosmic neutrino background, which is actually something suggested by my colleague Gil Holder here. And the result here that you find is that the angle, the RMS bending angle, is about 5.3 arc minutes. People have worried a lot about the lensing of the cosmic microwave background, and that's actually calculated to make 2.7 arc minutes. So the neutrinos are roughly double here, this calculation. These wiggles here are very important here because there's not that exact a calculation. But there's physics reason why the cosmic microwave background is smaller, which is that in the early universe, the redshifts around 10, the intergalactic hydrogen was reionized. That led to a lot of photon electron scattering, which interfered with the lensing of the background. So the lensing of the cosmic microwave background took place at smaller redshifts, that means later times than redshift of 10, whereas neutrinos were scattering all the time. Now you may say, well, the ionization certainly gave you a lot of electrons. The electrons can scatter neutrinos, but again, electron neutrino cross sections are very small, and so that turns out to be quite insignificant here. This is just a picture of the neutrinos propagating from early time, so showing their paths being the cosmic microwave background being bent here as it goes through the universe. Okay, the same picture again. Okay. So what we find here, if this just summarize the calculations here, is this is showing the bending angle as a function of the neutrino mass. What I've written down here is the results. What I wrote earlier was if the neutrinos are basically massless, but if you worry about the mass and the fact that 2 of the 3 are non-relativistic, then what involves here, instead of a factor 4, this is velocity times velocity plus 1 over velocity squared, and the spin rotation involves velocity minus 1 over velocity, which the spin rotation with respect to momentum. So if the velocity is 1, this angle is 0. And so the results are here. What you see here is the momentum bending, as the neutrino mat becomes heavier and heavier, the momentum bending goes up. The spin bending, on the other hand, goes down because non-relativistic neutrinos do not have the spin bend, and the difference of the two keeps going up here. And so you find, depending on the neutrino mass, somewhere between an angle 10 to the minus 5 down to here, for a neutrino mass of a tenth of an EV, of an angle of 10 to the minus 2 radians. So these can be significant here.
Gordon, there is a question from Paul Davis.
Hi. Okay, good. Paul.
Yeah, I'm not sure this is the appropriate time. I'm sorry, but I'll ask it anyway.
Okay.
What happens to neutrinos emitted from black holes by the Hawking effect? Do they come out with random helicities?
I don't know. I do not know.
Because there's no weak interaction source there, you see. So
that's a very interesting point. And
sorry to have interrupted you, but
no, that's a wonderful remark. I'll talk about neutrinos emitted shortly from neutron stars and supernovae, but I haven't considered neutrinos emitted from black holes. That's great.
Right. I'll be quiet.
The reason one gives seminars is to learn, and I think that was very good. Okay, so this is just to put all 3 together, looking at the spin rotation from gravitation versus magnetic fields. The gravitation result is shown here in the middle. This again is RMS angle. So we saw the same picture here versus neutrino mass. If the magnetic moment was a standard model, then the rotation from, I just did quote Milky Way calculation here, taking parameters I took for Milky Way earlier. This shows the galactic magnetic field, the spin rotation is much smaller. On the other hand, if the magnetic moment is large, then rotation from the magnetic fields, even the Milky Way, this is at 10 to the minus 14, which is a factor 1,000 smaller than the xenon 1-ton magnetic moment, then this is a rather large rotation angle one can have here, much larger than the gravitational rotation here. So this is the basic summary of the calculations, this picture here. Okay. Now at this stage, I want to get to the nasty question of how do we go about detecting these relic neutrinos? As I said, none has ever been detected. and it remains a big challenge. So one experiment, which was actually proposed by Steve Weinberg almost 50 years ago, is to look at inverse tritium beta decay to detect the neutrinos. Now, tritium beta decay, the tritium has a half-life of 12.5 years. It decays into helium-3 plus an antineutrino and electron. The there's a positron, yeah. This 12.5 years is very interesting because from a condensed matter standpoint, 12.5 years was the time after the Second World War when Landau wrote his theory of Fermi liquids. And it marked the time when one really had enough helium-3 to begin doing experiments, because the tritium that was developed at the end of World War II was beta decaying in sufficient amounts to give enough helium to do experiments here. So it's a history of physics and nuclear lifetime connection. Now, the inverse tritium beta decay, which has actually never been observed in any form whatsoever, you take a neutrino, hits the tritium, goes to a helium and an electron. So the trick is, what you want to do is detect the electron to measure the neutrino. There is something called the Ptolemy Experiment, which is ongoing, which is the Princeton something observatory. It's a wonder. It's Princeton Tritium Observatory. I don't remember what the rest stands for, but it's an ongoing experiment which is still calibrating, where they plan to use 100 grams of tritium to measure the electrons. And what you see in a normal beta decay spectrum, if the neutrino is massless, you would see an endpoint over here. If the neutrino has a mass, it carries, the spectrum is pushed to the left by the neutrino mass. This is in the standard beta decay here. In the inverse beta decay, however, what's nice is the neutrino gives its mass, provides energy to the total reaction Q, and so the peak gets pushed to the right here. There's a width of the peak, of course, because the neutrinos don't come in with definite momentum. But another feature that enters is the neutrinos do not have it. They come in 3 different mass states. And so if you look at the fine structure of this picture here, what you will see is that this peak is subdivided here into what you can measure. And the blue here is the inverted hierarchy, which has a large peak, a larger mass, and the normal hierarchy has a peak at that smaller mass over here. And I'll explain why that's the case here. So since one since the inverse tritium beta decay couples to an electron neutrino, the neutrino that comes in with a mass state I, its coupling to the electron neutrino will be weighted by this matrix element UEI squared here. Okay, so here is the cross section for the inverse tritium beta decay, Fermi coupling constant velocity. This is the standard CKM matrix. The U is the PMNS matrix. F is the Fermi Coulomb correction, masses. A here is 1 minus or plus velocity. This is the helicity dependence. And F here is the Fermi coupling constant for Fermi form factor, G is gamma of Teller. What is marvelous about this equation is the number of F's in it. If you look at the GF over here, then there's a Fermi over here, and find that the Fermi form factor over here. He really did quite a bit. It's quite amazing. Okay, and so the total rate here, what it has to do is average to find the rate at which you average the cross section times the velocity. Well, there's a velocity over here, so that drops out of the right-hand side, and you average this over the distribution of neutrinos, which, as I mentioned, is relativistic with the present temperature, even though the two of the 3 species are non-relativistic. Okay, so let's look at this in more detail. If you look in here and ask what depends on the neutrinos themselves, it is the matrix element, UEI squared, and then the helicity term over here. And so one can look in the average rate, one can ask, how does that enter? Look at what defined called A effective, which sums over the masses and helicities, the U's, the A is 1 minus plus A is 1 minus plus V, and the spin rotation as well, the probability of helicity negative and the upper sign is probability of positive helicity. The cross terms vanish, and what you get is 1 plus the average of VI squared cosine theta. Now, the sum of UI squared with a 1 is just 1. That's trivial. If you do the same calculation for Majorana neutrinos, both neutrinos and antineutrinos contribute, and then these factors cancel out completely. You get a plus sign here and a minus sign here, and the result is that the Majorana A effective is always just 2, nothing else, no further structure. And so if you look just at looking here, this, say the Majorana is 2, and the Dirac has 1 plus UA squared times the mean velocity. This is if there's no rotation. The picture you would expect, what you would find is that if you look at the A effective that enters the tritium beta decay rate, inverse tritium beta decay rate, versus the mass of the lightest neutrino, one finds pictures like this. The T here shows the present neutrino temperature, and so neutrinos, this region of the picture is for non-relativistic neutrinos. The left-hand side is for relativistic neutrinos here. I just repeated the velocities down here. And so what you see here is that you have to ask, when is this large? Now, if we look at it, the inverted hierarchy, the M1, I'm sorry, M3 is the lightest. M3, however, couples very weakly to the electron. So there's very little effect over here. So the 3 here, the 1, which has a large velocity, couples very weakly, and the other 2, which have rather small velocity, the 20th, they have small velocities, even though they couple strongly. The net effect is that in the inverted hierarchy, there's basically no interesting effect here whatsoever from the velocity. On the other hand, in the normal hierarchy, there's a rather large effect here, of almost a factor of 2 difference in the rates one can have. Now let's ask the question, what happens if you include spin rotation from the various fields here? What I've shown here is just 2 things. One is putting the cosine of the angle. The Majorana always remains 2. That's never interesting. It's interesting, but there's never any effect of rotation. If you put the cosines in here, cosine can be plus or minus 1. That would give the upper curve here, minus 1 would give the lower curve. And these 2 curves really bound the results here. Everything must lie within this region here. Here's an estimate if you take, quote, the Milky Way rotation, 10 microgauss with a magnetic moment of 10 to the minus 14, you'd find some reduction over here. Now, the question is, how do you observe all this? The interesting region is here, where the neutrinos don't have too large a mass. If they have too large a mass, there's no effect. If the mass is too small, it's very hard to resolve let me back up just one slide here. I should have, wrong way. Ah! Oh, sorry. No. Yeah, I wanted to show this picture here. If the mass is too small, it's very hard.
I don't think we see the picture.
No. Thank you. Sharing is paused. Stop share. Share screen. Zoom. Share. Thanks, Igor.
Yeah, it's fine.
I'll make it big again. Okay, I just want to remind you that if the mass of the neutrino is too small, this peak becomes very hard to resolve here. In fact, 1 EV resolution is sort of state of the art now, and we're looking at 1/100th of an EV at best. So this being able to resolve these peaks has become is a challenge for the future, not for theorists, but for the experimentalists. Here. Okay, so returning to this picture, to high neutrino mass, there's no effect. To lower mass, you can't resolve. And so the favorable region is in here, over here. And this is what you would like to be seen, to be able to see these effects. As I've said, this is in the future, because at present, one has never seen any inverse beta. These neutrinos have never been detected, much less resolved. And the inverse tritium has never been seen here. Okay, but so this is the present experimental situation. I want to just mention two very quick things. One, you can ask the question, what happens to neutrinos from the sun? Neutrinos from the sun, this neutrino energy, are primarily the pp neutrinos from the two protons going to deuterium plus positron plus neutrino. They're made primarily at solar radii of about 1/10 of the radius of the sun. And so you can ask the question, if a neutrino comes out towards us here, R0, Y0, how much does this get bent through interaction gravitationally get bent from interaction with the mass of the sun? Well, you can actually calculate this exactly. If you fix the point where the neutrino is emitted, then you just integrate along the path length the gradient of the gravitational potential. There is, unfortunately, this gamma v squared in front here. And this becomes an integral you can do numerically over the mass distribution of the sun. Mass distribution density looks like this, and one has a distribution of source points here. And when you integrate all that, you find the mean angle squared is like Gm over R. This is Gm over R is half the ratio of the Schwarzschild radius of the sun, which is 3 kilometers, divided by the radius of the sun, 6/10 to the 10 centimeters. And so you find something rather small. However, if you look at light neutrinos, this angle can be very large. This is probably beyond the range of detection. However, you might ask the question, maybe there are dark photons or other funny heavy particles that come out of the sun with spin. Those particles, if they're massive, could be significantly rotated by the gravitational magnetic fields of the sun itself here. Okay. Back to Paul Davies' question about the neutrinos from this. Even if they're made in helicity eigenstates, which is not very likely, they are not all traveling radially out from the sun. They're traveling some will be there'll be a spectrum directions, and they will certainly undergo gravitational rotation as well here. Okay. Next question you may ask, what about neutrinos from stars in diffuse supernova background? Now, this is an interesting experimental question. There are many supernovae that have gone off over the cosmos, which have emitted a lot of neutrinos, mostly in the MeV, 10 MeV range. These form what's called the diffuse supernova background. And these can be detected, and Kamiokande is actually in good condition, is in good shape to detect these through the inverse ordinary beta decay reaction, antineutrino proton, positron plus neutron. And the question is to detect the neutron, and they have recently doped the detector with gadolinium, and the gadolinium absorbs neutrons, giving out lots of low energy gammas, and these gammas are readily detected. And so this is an experiment that will be done. And if you just calculate the rotation angle, just from the magnetic fields of a neutrino coming out from a neutron star supernova, just roughly mu b r over c, it's a very, most naive estimate. You write this in units of 10 kilometers, magnetic fields in units of 10 to the 12, neutrino magnetic moment over the Bohr magneton. This is 5 10 to the 13 here, which is comparable to what we found from galaxies, 5 10 to the 14 over here. What's interesting here is this scales, the distance scales are, but magnetic fields in supernova, as they collapse, making neutron stars, and early neutron stars, magnetic field will scale from flux conservation as 1 over the scale of the size squared. And so this r times a 1 over r gives r squared gives a 1 over r, which means that the rotation is largest from neutron stars rather than supernova. Here. The gravitational rotation of the spins is negligible because these very large factors of Lorentz gamma, some 10 to the 8, 10 to the 9 that enter here. but the magnetic rotations are interesting here. So let me just conclude here by saying that the relic neutrino helicities are a potential new probe of cosmic gravitational and magnetic fields, which will be explored as the neutrino detection technology improves in coming years. One finds significant changes of relic neutrino helicities for magnetic moments even 3 to 4 orders of magnitude smaller than what the xenon one-ton experiment suggests. The neutrino magnetic moment may be much smaller, but it may be much larger. We just don't know here. And gravitational helicity changes are much, much larger than the standard model, what you find the standard model if the magnet with a small neutrino dipole moment, but they're much smaller than you would find with a much enhanced magnetic moment. So you'd find the gravitational rotation is the same picture, sits between galactic, between magnetic rotation for small magnetic moment, magnetic rotation for large magnetic moment. But as I want to close, last word is one really needs significant improvements in the electron energy resolution to be able to resolve all this physics experimentally. And so we're not there yet, but I'll lay it out for the future. Thank you very much.
Well, thank you very much for your very nice presentation. Now we will have some time for questions. I see first raised hand by Cecilia Lunardini, so go ahead.
Yes, hi. Great talk. I really enjoyed it. Thank you so much. I'm curious about the gravitational effect. If I have a supernova that explodes and emits a lot of neutrinos, and the neutrinos pass close to a supermassive black hole, what would be the scale of the angle? Did you think about it?
These are relativistic neutrinos, but I guess my very first slide, like if I can get there without losing the connections here.
So I was trying to think of the strongest gravitational source I can think of, which would be a supermassive black hole.
But these results here, showing the gravitational rotation, 2mg over gamma v, impact parameter v squared, this holds perfectly well for black holes, as well as, yeah. And so if they're supermassive, this could be super.
So okay, so you don't have a number, but it's easy to just plug in the numbers, I guess.
Well, I give you a number. You tell me what mass you'd like.
10 to the 6 solar mass black hole.
10 to the 6 solar mass.
Yeah.
And what,
distance 10 to the 14 centimeters.
and what is the impact? Yeah, parameter.
Yeah, 10 to the 14 centimeters.
10 to the 14 centimeters.
Yeah.
That's a factor 10 to minus 3.
Okay.
But insignificant.
Okay.
But more importantly, what are the fluctuations? I mean, the ones that go closer are the ones are more. The average is not important. It's the ones that go closer that become interesting. So you really want to calculate a spectrum.
Yes. There is a spectrum. Yes. Okay.
Please do it.
Interesting. Okay.
Yeah.
Okay, that's interesting. Thank you.
Thank you. Yeah.
Okay. Next question, Tanmay.
Hi, Gordon. That's a very nice talk. I enjoyed that a lot. So the neutrinos would be affected.
The seeds you planted. The seeds you planted earlier, yeah.
So maybe let me continue that seed, hopefully, into a tree. So the magnetic field affects the neutrinos, but the neutrinos must be affecting the magnetic field. If the magnetic field affects the neutrinos, then the neutrinos must have some sort of back reaction on the magnetic field.
Yeah, I mean, these guys are streaming along with a magnetic moment with an associated magnetic field, yeah. But the trouble is they're streaming in all directions. They're basically isotropically distributed. And so neutrinos going this way and this way will produce fields that will cancel.
I see. So you're saying on average, it would all wash out.
Except on sort of interneutrino distance scales.
see.
Yeah, but it's my guess is probably not important, but it's again something good to think about. Yeah.
Right. The other question was neutrino oscillations don't play any role in this exercise.
That's a good question. The answer is no. We actually went through that. That was an interesting month, learning about MSW effects and such. There are certainly MSW effects in the early universe, but they don't affect the neutrino distribution when you come out. They come out with this relativistic distribution. You know, the masses that enter are affected, but the masses are so small compared to the momenta that those mass modifications don't play any role.
Nice.
Because they're coming out with 10 MeV, whereas the mass modifications are at the sub-eV scale.
Okay.
Yeah.
Thank you.
That was disappointing.
Next question, Kohei Kamada.
So regarding to the first question of Tammei, is it correct to understand that chiral magnetic effect happens also for neutrinos?
Oh gosh. I guess so, yeah. But I've not thought about that one at all. That's again.
Well, it's a bit confusing for me because chiral magnetic effect is often said to be from the chiral anomaly, and chiral anomaly is often said to be one loop exact. So I wonder for neutrinos if one loop effects can happen.
If I may interject, I believe it's simply the interaction with the magnetic moment. It mimics the chiral magnetic effect, but I don't think it's literally the chiral magnetic effect.
Yeah, that's well put. But again, those are some calculations worth doing. Yeah. Yeah.
So practically, we will have the suppression of the neutron magnetic moment to compare to with the usual chiral magnetic effect. Is it correct?
Say again?
So practically, the efficiency of the induced current is suppressed by the neutrino magnetic moment. Is it correct?
The chiral current will be suppressed by the magnetic moment compared to the usual chiral magnetic effect, I guess. That's the question.
But it is just a mimic and it's not.
I don't know. Yeah.
I mean, the neutrinos are neutral, so so there's no current as such, I would think.
Well, you could think of helicity current or something, I don't know, but there is definitely ordering of magnetic moments in the magnetic field.
Yeah, so well, what I have in mind is that back reaction from the neutron to magnetic field, then it would appear something like chiral magnetic effects. This is what I have had in mind. So
Well, there could be some analog. Yeah, that would be interesting.
Yeah.
So yep.
Good.
Well, I see this is developing into a new research direction, which is nice.
Yeah, okay. Yeah. It is quite interesting. Thanks.
Any other questions? Any other questions? Actually, I did have a question of my own. When we were talking about the cosmic effect on the neutrinos, you were saying that there was this helical fields that have basically no effect. It was a bit puzzling kind of thinking about it. It naively would say that if there is a helicity, then it would be coupled more naturally to the helicity of neutrinos, and therefore you would be maybe not changing or flipping the helicities, you will be simply producing more, let's say, left-handed rather than right-handed neutrinos in the presence of such a field. Isn't there such an effect?
You mean when the question you're asking then is when neutrinos decouple, what were the helical fields affecting their production rate?
Well, something like that, yeah. Or basically even turning from one helicity into the other helicity simply because we have sort of like a helicity conservation of sorts that would go from the magnetic field to neutrinos.
But
To me, it seems like a
I
very
don't know.
local effect. So it's hard to see how the global twisting of the magnetic field would. I don't know without actually doing it, but
I mean, it's hard to take energy out of the magnetic fields here.
Well, they're interacting via magnetic moment with the neutrinos, so it seems there is a direct channel.
Yeah, but you would.
That's what most puzzling to me, that you don't have any effect.
No. Well, all I noticed here is this is simply drops out from the fact that the gradients are odd it drops out of the integration of the neutrino through the helical field over time. But I certainly am open to smaller scale effects, but I just don't know. It's good.
Okay, I probably have to think exactly about the mechanism anyway.
And let me know what you come up with, because it's a good question.
Right. But we have other questions, so I don't want to just steal the show. Ching Yang, you have a question?
Yes, hi, Gordon. When you're talking about gravitation, and then what about the dark matter? I mean, we don't know the interaction strength, with other interaction, but if they have a mass.
Yeah. That's all in here.
Oh, okay.
The Planck measures density fluctuations, which can be dark matter or
can be anything.
Whatever. Yeah.
Great. Okay. Thank you. I always enjoy your talk. Thank you very much.
Thank you. It was good to see you.
Yeah.
Okay. Any other questions? Any other questions before we wrap this up, so that everything is resolved? And
so Igor will have my slides
yeah, I'll post them, and you will find them linked through the webpage, through the Inspire, and everywhere.
So please pick apart these calculations, suggest improvements, because this all first approximation by an amateur going through the field, and there's a lot more work to be done. I mean, certainly doing galaxies beyond the spherical galaxy approximation and such. There's some real calculations that need doing here.
Okay, I don't see any questions. So before everybody goes, I want to use this opportunity to thank you, Gordon, for a very nice presentation and lovely discussion that he generated here. And thank you.
Thank you too. Thank you, my audience too.
And thanks everybody for coming. It was a great talk.